Welcome to a new video about power electronics. In this example we will discuss the type 2 compensator for the buck converter. In the previous example we have looked at the design of a type 3 compensator, so this is another example where we use a type 2 compensation. Of course we will see how we can generate the plots and also the calculations step by step, and also verify this in MATLAB Simulink and also in TI SPICE simulations. Okay, now before we dive into the topic, let's give a very brief overview of the theory we need. So we'll talk about the phase margin and gain margin, also about the circuits here, about our transfer functions. And also we will use this circuit, which is the type 2 compensator. Okay, first we discussed about the frequency response analysis. We see here the loop gain, magnitude, and also the phase. Let's define first what the gain margin and the phase margin is. These are the stability margins. For gain margin, in order to have some gain margin, or calculate the gain margin, we look at the frequency where the loop phase, so this pink line, is minus 180 degrees. That can be determined from the body plot, or you can calculate that analytically. We will see that shortly in an example. That frequency is called omega gain margin, so this frequency. Then you go up and you look at that same frequency in the magnitude plot, what your loop gain is. Now, for example, if this is, let's say, minus 6, then you can go up by a 6 dB, so that is how much you can raise your magnitude curve to 0 dB. That is the gain margin. If you can raise it up, that means you have a positive gain margin. If you go down, for example, let's say 8 dB to 0, that means you have a negative gain margin. That means you have an unstable system. The phase margin definition, or the procedure for that, is find the frequency where the loop gain is 0 dB. So you actually start with the blue line, determine where the loop gain is 0 dB or unity, so 1. That is the phase margin frequency. Then we call that. You go down and look at the pink, which is in the phase of our loop transfer function. Then you determine how far you are from your minus 180 degrees. And this distance is the phase margin. It's just a number. If this phase is, for example, minus 100, let's say minus 150, that means you have a phase margin of 30 degrees. But if this phase is here, let's say minus 200, then you have a phase margin of minus 20 degrees. That means you have an unstable system. In order to have a stable system, your loop transfer function must have a positive gain margin and a positive phase margin. Okay, let's see an example that is always handy. So loop transfer function, a third order system is given by this. You see 3 poles, minus 4, minus 8, and minus 10. We like to calculate the phase margin and the gain margin for this circuit or the system. So how do we do that? Now, first we start with equating the magnitude of this loop transfer function to 1, which is also 0 dB. So we just solve that. That means take the magnitude of this one is equal to 0. You can solve this just using your calculator or any solver. That will give you an omega of 6.79 radians per second. And this is now the omega PM, which is the phase margin frequency. Now we're going to need to go down and also determine now the associated phase with this one. So that is the argument of that loop transfer function determined for that specific frequency of 6.79. So then we get this minus 134 degrees. How you determine that is the following. The phase contribution of the numerator is 0 because it's just pure real part. There is no negative sign, etc. So no imaginary parts. Each part of the denominator will give you then minus arctangent of the imaginary divided by the real. That's actually what you see here. And then you substitute here the omega PM, which is then 6.79 radians per second. Okay, now that means I'm now at minus 134 degrees. That means here the distance between the 180 degrees and the minus 134 degrees is 64 degrees. That means this is my phase margin. So this is the margin or the safety I have from the, let's say, the part which I don't want to be. The gain margin is in a similar form, but then we start with the phase expression and equate that to minus 180 degrees. Actually, you start here. So at the pink line, and then you can solve this and you get here 12.33 radians per second, and this is now the gain margin frequency. Now we take this value and substitute that in the loop transfer function magnitude, and that will give you, you can see that here, we give you 0.3307, or in dBs minus 9.61 dB. And this is exactly what I meant in the beginning in a general discussion, that this is now the minus 9.61 dB, so you can raise it by 9.61 dB, so plus, in order to get the 0 dB line. So we have now a positive gain margin. So looking at the results, the phase margin and the gain margin, we have now a stable closed loop system. Let's see that also in the simulation, because that is also interesting. This is the Bode plot generated using MATLAB. Using the script here, you see here definition of Laplace transfer parameter. This is the loop transfer function we have here, and we have now the Bode of this loop transfer function. Now you can look at it that the gain margin here is 9.61 and the phase margin is 64 degrees, so as we have calculated. So this is in agreement with our calculations. Okay, let's now first also look at the control circuits before we dive into the actual design of a type 2 compensator. This is the circuit which you can use for your buck converter in the AC model. You see here the equivalent series resistor of the inductor, and similar for the capacitor, and this is the load resistor. This is the switching part, and now we have the feedback here which goes to the error amplifier, has a reference, and then this error amplifier will then compare the reference and this output voltage, and then it will then pass its signal, error signal, to the modulator, which then drives this gate driver, which will then change the duty cycle of the switching. That's the whole process actually in a nutshell. And that will be then given in this controller block diagram. You see here the switch, the filter and load. This is just a transfer function of this from here to there. You see here the VS, which is of course the input for the switch, and the output is the part of the input, which is then the duty cycle times the VS. You see here the PWM, I mean, so this is the modulator and the error amplifier, and then you see the complete loop. Okay, let's see first what the type 2 compensated error amplifier is. This is the type 2 compensated error amplifier. You see here the reference signal and our R1, R2 and 2 capacitors C1 and C2. This is the Bode plot for the magnitude. You see there is a pole at the origin. Let me first discuss this. And also 0 and another pole. So we have 2 poles and 1 0. You can also have a type 3 compensation if you need more phase contribution, so more flexibility. You can go for this one, so that's actually an addition of the 2 components here, R3 and C3. We have discussed this in a separate video, so you can also look at in the video description of this video to find more details about that. And then we have a Bode plot which has a shape like this. Now the transfer function, what we need for our discussion in this video is this G2. We see here again the 0 and the pole at the origin and pole at omega p specifically. And this is for the type 2 compensated error amplifier. Okay, now let's first look at what the modulator means. Modulator has a reference signal which is then our ramp, so it goes up and down like so, and we have a control signal which is then controlled, and that will be then compared to that ramp signal. Now the difference between these two will be then evaluated or put at the output as the modulating signal. So you can actually see here the blue line and the red line will be then compared, and if the red line is smaller than the blue line, so if the blue line is larger in value than the red line, so you have then actually the value which is then the V modulation is then high. And when the red line goes high, then you go down, so the modulation will go for example to 0 and then goes up, and depending on the control signal. So if the control signal goes up, so higher, we need more compensation because the output voltage, for example, goes to a lower value than we need it. Then the duty cycle increases. That means the switch is closed more longer for a period, and that means we need to push more energy to the output. And you see that the duty cycle is then also increasing. Now the transfer function for the modulator can be calculated and determined from the average output voltage, which is then this general formula we know. And that is again calculated using the on time from the 0 to the on time itself. This is actually exact same expression as we have for the buck converter itself. But for the transfer function, we need to look at the changing. So the changing in the modulating signal divided by the changing in the control, because the ramp signal is a constant change. So this is changing. The change here is actually a dynamic, and the change in the modulation is also dynamic. We can also write it down in a mathematical form in this form. It can be written also like so, and that will then at the end result in a form which is pretty simple. Vs, which is our input DC voltage source, over the ramp amplitude, which is then the amplitude here of the red signal. So this is an important transfer function we will use later. Our filter and load is this part, which is then the AC model for our buck converter. Now the filter and load transfer function is then given by F, which is VO over the diode voltage here. So there's the input for our filter and load circuit, and that is after some algebra and circuit analysis, you end up to this expression in the Laplace domain, which is a second order transfer function having 1, 0, 2 poles. The compensator itself we need is the GS, which is actually the error amplifier, so which is then VC, so from here over VO. Everything is of course in the Laplace domain here. But that is also looking at the error amplifier itself, which has an open loop transfer function, also depending on the frequency. And there is also this feedback element, which is around this error amplifier. So that is also what we need to consider. But the error amplifier has an open loop transfer function, which is given by this expression, which is a first order model. And most of the time, the beta times the open loop transfer function is pretty high, so much larger than 1. So looking at this transfer function, we can say this can be approximated by this expression, because this 1 is pretty small compared to that product. Or you can also say 1 over the beta. Now we can say that 1 over beta is close to the actual transfer function of our compensator transfer function. And the feedback transfer function, that is the feedback element, the passive elements around this, that is the beta. Okay. Let's now go to the calculations for our discussion. So we have now a practical situation where we have a DC input voltage source of 20 volts for our buck converter. The average output voltage we want is 8 volts, and the average output current is 2 amps, and the maximum percentage peak output ripple is to be 0.1%, so pretty small ripple. Now that is done, and then the buck converter component and the values we have then selected are these. So we have an inductor of 200 microhenries, which has a equivalent series resistor of 200 milliohms, and the capacitor will be then 100 microfarads with this 500 milliohm ESR. Now the resistor, the load resistor, must be 4 ohms, because that is 8 over 2 minimum, so you can go up, but that is really the minimum value it's allowed, and we have a switching frequency of 100 kilohertz we have selected. Now the design objective we want is the type 2 compensated error amplifier and for a stable control loop system. And we need to design for a crossover frequency which is then 1 decade smaller than, in this case, 10 kilohertz, because 10 times smaller than this 100 kilohertz we have selected for our switching frequency. And the phase margin we need to target is 55 degrees. And this is again the general diagram for our control loop. And we can see now here in more detail what we have. So we have again the switch and the filter and load, but now we have an output which goes now to this compensating network. Which you have here is all the error amplifier, where you have also the reference. So this complete part is the compensated network, and the R1 and R2 will create the voltage division, which will be then compared to that reference signal. And the PWM generator here is the generator we have discussed, and there's also some transfer function here. Okay, let's see now the solutions for our design in order to calculate the components here, C1, C2, R2, and R1 and R3. So first we look at the filter and load transfer function. We already have discussed that, or actually shown you that. So we go first from the Laplace domain to the J omega domain. And then we need to also look at the modulator transfer function, which is already discussed, which is Vs over the re-ramp. Okay. So type 2 compensated error amplifier transfer function is given by this expression. We have already seen that, but now in more detail. You see here the resistors and the capacitors which you have here, except this R3, which is really just for division, so that is not included in this transfer function. But we know, and we can assume that most of the time the C2 is much larger than C1. So we can say the C1 is much smaller than C2, so that means C2 over R2 times C1 times C2 will be then 1 over R2 times C1. So that's actually what you see here. Now we have an expression which is simpler or easy to follow, because you can now recognize the 0 and the poles directly instead of looking at this a little bit more complicated expression. Now the loop transfer function will be then the L, which is the loop transfer function, not the inductor value, which is then the modulator times the filter and load times this type 2 compensated error amplifier. Now we can now add them, multiply them together, so we get a very long expression where you see the red, the blue, and the pink expressions here. and now also in the j omega domain. Okay. So we need to use this now in a more efficient way. So how we do, we first look at the phase, because we have some condition for our phase margin. So we need to look at the phase of the loop transfer function, which is then the argument. So the argument of our loop transfer function is the argument of our modulator plus the argument of our filter plus the argument of our compensator network, or the error amplifier in total. So that means if I look at the modulator is independent of the frequency, so that is, we have then zero phase contribution by M. The filter itself will have an expression for the argument given by this expression. You see here the arctangent of the numerator minus the arctangent of the denominator, imaginary value divided by the real value, but imaginary value divided by the real value will be a negative, so that needs to be, we need to add also 180 degrees there. This is another expression, and that will be also evaluated at the crossover frequency of 10 kilohertz. Now when you do that, when you substitute in this formula the 2 pi times the 10 kilohertz, so 2 pi times 10 to the power 4, and also using the RC here, and also RL, and the capacitor, and the resistors, etc., everything, you end up to minus 103 degrees. Okay, that means the following: the phase margin is given by 180 degrees plus the argument of that loop transfer function at that crossover frequency. So we have now the phase contribution of 0 degrees by the modulator, and also minus 103 degrees by the filter and load. So how much do we need to give or provide from the compensation? So this is then given by 55 minus 180 degrees will be then minus 125 for our argument. So this needs to be compensated, and also we need to go above such that we have this 55 degrees. So that means we need to follow this expression. So just relate this. That means minus 125 is equal to 0, because it is argument of M, plus minus then minus 103, and plus the argument of the error amplifier type 2. Now when you do the calculation here, you need an argument or the phase contribution by G2 of minus 22 degrees. But we know we have a phase inversion by this amplifier or this configuration circuit of minus 180 degrees already. So we need to add 180 degrees already. So we can say the compensation we need is minus 22 degrees plus 180. That means we need 158 degrees in total, considering also this inverting action. So we need to use this parameter for our design. As said, we need 158 degrees. So our magnitude will be also determined. So the magnitude of our loop transfer function is the magnitude of the transfer functions individually and then multiplied together. So the loop transfer function must be unity at that crossover frequency, because that's the definition of the phase margin. So we have now the filter and load transfer function, so that's the absolute value. And when you evaluate that at that unity gain frequency or the crossover frequency of 10 kilohertz or 2 pi times 10 to the power 4 hertz, you will end up to this value. But we need to have the product of these three must be 1. So the modulator gain is already given, which is 50, by the way, for our buck controller we will discuss shortly, which is LM5146. And then we have now the crossover frequency, the compensator, so the G2 needs to add the following gain, which is 1 over the M times the F, which is in this case 0.03742. So we need to have approximately 1.78 as the gain, which is in the dBs 5.02 dB. Okay, now we have necessary information. We know how much compensation we need in the degrees. We also know how much we need at that unity gain frequency or the crossover frequency for our compensation to add as the gain. Now the buck controller IC, which is the LM5146, which is what I have selected, is given here. We see already the components R1 and R3, R2 and C2 and C1. This is, by the way, a synchronous buck converter controller. You see here the two MOSFETs. We see here our inductor and our capacitor, which is our inductor L, and then C here actually, which is called C out. There's also C in here, so just to filter out some ripples if necessary from the input. Okay, this IC will then create that error amplification, etc. Everything here in that IC. We only put the components outside to create this compensation network. And there are now the specifications shown here. So we have a reference voltage of 0.8. There is some range of the input and output current capability. So all of the values are shown here. And also the PWM ramp amplitude is given by this VS, which is R20 over 15. So there is already a gain of 15 for the modulator part. So we need to actually divide by 15 in order to determine how much your VRAM should be. That is in this case 1.333 volts. There's also a value of the error amplifier DC open loop gain bandwidth product. Now using these values we can calculate also the pole for the error amplifier itself. And these are this is the small part of the table in the datasheet of this buck controller IC. You see again the gain of the PWM controller, error amplifier reference voltage of 800 millivolts, also this DC gain of the error amplifier, and also the gain bandwidth product. Okay, let's now look at the compensator values. So we will use the K-factor method to calculate the required values for our design. So we know that this is the transfer function we have. So we know that we have 1 0 and 2 poles, one of the origin, one of them at some specific frequency. Okay, we start with the first step, which is the calculation of the K-factor. Now K-factor is given by the tangent of the compensating phase, which is in this case 158 over 2. So if you do the calculation here, you get 5.1446. Now the next step is calculate the R2. R2 is related really to the inverting amplifier gain, so which is then R2 over R1 at that specific crossover frequency. So it means letting, for example, R1 to 10 kilo ohms, we can calculate R2 by multiplying the compensating network evaluated at the crossover frequency times R1. So which is just, you see that actually this is just a simple inverting amplifier formula, which is R2 over R1 is equal to the G2 absolute value. Now when you do that, you get now 1.782 times 10 to the power 4, which gives you now 17.82 kilo ohms. Step 3 is the calculation of the capacitor C1. That can be done using the formula here. We have the K, we have the R2 already, and we also know what the omega T is, which is our crossover frequency, of course, in radians per second. So 2 pi times 10 to the power 4, etc. So we have now here 173.7 picofarads. Next one is the capacitor C2. In a similar form, you see here, the only change is the K goes up, and then exact same procedure. In this case, we get now 4.596 nanofarads. The final one is the calculation of the R3 here, because we need to make a voltage division in order to compare that voltage node with the V reference. So it means actually following V reference over VO is R3 over R1 plus R3. So we can also say cross multiplication like so, and also in this form. So we can now evaluate or express the R3 in the other parameters, which is given here. We know what the reference voltage is, which is 0.8. We know what our VO is, which is 8, which is what from our specifications. So we can say, just substitute values here, we get now here 1.111 kilo ohms, so 1.11 kilo ohms approximately. So we have now everything. We have now determined our values, so we can go to the simulation results. First, we look at the MATLAB script. So this is the MATLAB script I have developed. You see here the definition of the Laplace parameter again. These are the specifications for our design here. You see the switching frequency. These are the buck controller IC parameters, the components for our buck controller, or I mean buck converter. And there is also here the transfer function for the modulator, the filter, and also the filter times the modulator. And the frequencies we have selected and also calculated. So the unit gain frequency or the crossover frequency is 0.1, so 10 times smaller than the switching frequency, which is just a selection. And all the other values are calculated here and given. So when you now do the calculations, etc., so then we get also what we have calculated here. So now when you now run this script and then do the body plot or loop transfer function for each of them, so the f is the filter, m times f is the filter times the modulator, g compensator is just only the compensator itself, and g loop is the total part, so that is the filter, the modulator, and the compensator. Okay, now we see here in purple the loop transfer function total. We see at 1 kilohertz that the gain is not exactly 0 dB, so it's not 1, so minus 0.32, so close, but still some error. And now you see also that the same frequency, you see that the phase is minus 124 degrees. So that means in this case we have, also looking at the compensator, the compensator itself, which is this yellow line, will add actually minus 22 degrees. We have actually also have calculated that, but it should be actually minus 22 degrees, so it is very close. What you see is that the phase here is, if you calculate that, looking and then considering this 10 kilohertz is the unity gain frequency, there will be then a phase margin of 56 degrees, because the distance from this phase to 180 degrees minus 180 degrees is 56 degrees. So okay, this is exactly as we want, or actually more than what we wanted. Okay, now let's also look at the simulations in TINA TI Spice, but then using the real circuits. So this is now the circuit in TINA TI Spice. You see here the AC model of our buck converter. You see here the inductor, and it's also its ESR for the capacitor also, and also we have our 4 ohms as the load. We have here the modulator, which is the voltage control voltage source, 15 as the gain. See here the C1, C2, so these are the values. We have also the R2 here, R1 for 10 kilo ohm we have selected, and we see here the R3 we have calculated because of this reference voltage here. And this is the error amplifier. We see here the open loop value of the error amplifier, which was 49 dB. So we went to from 49 dB to this value from this. So you can also see that 49 dB. We went to 50,119. And we have now here also created a pole, which is 130 hertz approximately. So I've just selected this 1 kilo ohm and then calculated this compensated capacitor using 1 over RC formula. And we need an inversion because we have an inverting amplifier configuration. Now this complete part circuit is then the model to check the phase margin for our buck converter and the controller in total. Okay, let's see now the loop transfer function together and also everything. So we see here in green, which is only the filter. In this brown or dark red, we see here the filter and the modulator combined. The compensator itself is only the pink one. And the blue one is what we want as our loop. So that's actually more important. Now we see here the loop transfer function is, in this case, has a crossover frequency, which is this blue one, is 9.62 kilohertz, which is not 10 kilohertz. So it's a small error, let's say approximately 400 hertz. At the same frequency, we have at the loop transfer the phase of 54 degrees. So it is actually in the TINA TI Spice, it's always positive. So we actually ignore that 180 degrees. So we see actually here already that this is 54 degrees as a phase margin, which is a little bit smaller than the 55 degrees we wanted. So still close. So we can say this is perfect. We also see that the compensator itself will add 157 degrees instead of 158 degrees. So there's a small error there, so that will also translate that to error here. But it's all close, so that is perfectly fine. And see again here the phase margin of 53.8, so let's say 54 degrees at that crossover frequency, which is smaller than what we have anticipated. But still fine, so we can say the phase margin of 55 degrees is not achieved, but it is very close, so we can say this is 54 degrees. Alright, it was our example concerning the type 2 error amplifier design for our buck converter. We have calculated the required values for the compensating network using the K-factor method, and we have also verified our calculations using MATLAB, and also in this case the TINA TI Spice model using the actual components and also given here the Bode plot for the loop transfer functions. If you have any questions, comments, please let me know. I will try to answer them as soon as possible. Don't forget to like and share these videos so that we can reach more people for these interesting topics. Thanks for your cooperation and see you next time in another video. Take care.